In this video, we'll be talking about hyperparameter tuning, which is a technique of choosing a set of optimal parameters for a learning algorithm. Let's move forward. Look at an XGBoost example to explain hyperparameter. You will see that XGBoost is a machine learning algorithm, but you need some parameters for the algorithm to learn your data, or when you're training, for you to learn the process and be able to predict accurately. So one of the parameters, we have the max depth, learning rate, subsample, column sample by tree, then we have gamma, and there are many other hyperparameters that you have. But what we need to tune when working with XGBoost, for example, they are the parameter ranges of each of those hyperparameters. So you have, for example, typical boundaries. You have 3 to 10, which means you can tune your max depth from numbers of values between 3 to 10. You can use 3, 4, 5, 6, 7, 8. And you can do that for other kind of hyperparameter that you have in XGBoost. But the challenge here is, how do you know which parameter is optimal? Now, to achieve that, that is why you do hyperparameter tuning. And to do hyperparameter tuning, there are three core techniques to achieve it. Number one is using the grid search. And if you look at grid search, it is exhaustive. So it exhaustively evaluates every combination of hyperparameters you specify in a predefined grid. And this is the example. So let's say this is the optimal parameters that you're looking for. You will need to go through each of the parameter options that you define in terms of their combination and go through each and test each until you arrive at the optimal parameter. And doing this will take a lot of time, and that is why it is exhaustive. When we show it in the code, you will see the example of what I'm talking about. The next one is the random search, and for the random search, it samples random combinations from hyperparameter distributions instead of checking every possibility. So it will go randomly and check the combinations until it arrives at the optimal parameter. So this takes lesser time than the grid search. However, this doesn't really have a pattern of searching through the parameter because it is very random. That is why we have the third one, which is Bayesian optimization. And when you look at Bayesian optimization will build a probabilistic surrogate model, for example, using a Gaussian process, and have an objective function. So the objective function is, for example, in this case of classification, you can have a cross-validation accuracy. In the case of regression, you can have RMSE, MAE, MSE, as you deem it fit. And then it uses the past evaluation to predict promising regions, then balances the exploration. For example, it will detect the uncertain areas, then explore the known good areas. Then it updates its beliefs and iteratively continues the process until it arrives at an efficient convergence. And this is the example. So when you look at this hyperparameter combination, it will first check this, then learns using this that this is really not a certain area. That is, it is an uncertain area to find the best parameter. So instead of checking each, it will then go a bit far away from the uncertain area to then look at, okay, can I still find the parameter combination? Then if that is not possible, then it will conclude that this is an uncertain area, then move to another far range because this doesn't look certain. Then it will then test, but it is always checking it with the objective function to determine if the area is certain or if it can find the optimal parameter in the area. So when it checks this and sees that I've seen this part, it is uncertain, the next that is very close to it is uncertain, then it will move again into a similarly good area. So if it checks this area and finds that, oh, this area is a bit closer to achieving the optimal hyperparameter, or for example, this area is closer to fulfilling the objective function that you defined, then it will continue to search in that good area. You can see it will move, let's say, 2 steps and continue to notice that it's getting close, and it will continue that process until it arrives at the optimal hyperparameter. So when you look at this now, the process it went through is not as much as the random search or the grid search. And that is why this is a very nice process or a very nice optimization technique to use. To demonstrate it, we see how this works in an animation that I've prepared to just make the explanation clear. So you look at the grid search, it continues to do that, check each hyperparameter combination until it arrives at the optimal hyperparameter. And when you look at the random search, you will see it goes randomly. There's no specific pattern for it. So it goes randomly, and you can see that going until it arrives at the best hyperparameter. So you see that continues, then arrives at the best hyperparameter. Now for the Bayesian optimization, just like I've explained before, you can see it keeps searching, then keeps searching until it arrives at that point, and you can see the pattern of the search. So to see how this really looks, we'll move into the code so I can show you the hyperparameter tuning in practice using the grid search, random search, and Bayesian optimization. For this hyperparameter tuning exercise, we'll be using the data used for the crop type recommendation project, which has been uploaded last week, and you can see it somewhere on the screen for you to check the whole project. And in the project, I've explicitly explained how to do classification of crop type in machine learning. And here in this video, we're going to be using the data. So we're going to be getting the data from Cargo and using Cargo Hub. And we have our library, pandas, and NumPy that we use NumPy for mathematical operation and pandas for manipulating our data frame. Now I'm going to load that to get the path. Now the path is loaded, and this is the path where the data is. So all I just did was copy this path and use this terminal command called ls, which is to list what we have in a directory. So it's going to show us all the file in the directory. And you can see that now we have the file crop recommendation.csv. And to do that, we just need to get this directory and attach the crop recommendation.csv to it. And you can see this now, and we will run it and check our data set. And that's it. We have our data set. These are the label of the different kind of crops. You have rice, you have different kind of crops. Then you have the nitrogen, you have the phosphorus, and you have the potassium, the temperature, the humidity, and pH. So these are like the soil properties, and you have the climate properties of the area. Also the pH of the soil and rainfall, for example. So the next thing we do for our machine learning will be to split the code. But before doing that, we're going to be needing Optuna for our Bayesian optimization. So we're going to first install Optuna and wait for that to load. And that, I think, is successfully installed now. So we can move on to the next thing. And here we need this libraries, for example, sklearn model selection. So to use our random search, using random search CV, our grid search. Then we need our cross-validation score, the train test split to split our data. We have Optuna installed, which has now been imported. Then we have our sklearn.preprocessing, where we imported label encoder. And the label encoder they use is for us to encode these labels into numbers or into numeric values. So because for machine learning, it's understand numbers, not necessarily the text directly. So, and we imported XGBoost here. So I'm going to be loading the libraries and just run this line of code. And this line of code, we're encoding the label, then we fit using the label encoder. So we fit the label. So that is how you do the label encoding. So you first instantiate the label encoder here, then you assign it into the label encoder column so that it will replace the current label with the new numeric value label. So then we have our X. Our X, they are the predictors. So that is the old data set without the label. Then Y is the label that we're going to be using for the machine learning algorithm to learn and then predict the same label in the next phase. So here, to divide the data set, you're going to be dividing the data set into training, testing, and cross-validation. So for the training, we are going to have the X training. We take 10% of the old data set as the text data set. Then we have the training data set where we're going to be getting the train and the cross-validation data set. So to do that, we're going to be using the 20%, which is 0.2 of the data set of the training data set as the cross-validation data set, while the 80% will then be the trained data set. We use stratify equals y because we are dealing with classification. So we want our labels to be balanced. So it's going to stratify them accurately so that in testing, you're going to have some crops existing. In training, you will have the same amount, a number of crops existing. So you're not going to have this mixed match where training data set has some crops and the cross-validation data set lacks those crops. So we run this to see that, and now we move into the hyperparameter tuning itself. So I have the code here. The first is we need to instantiate our XGB model using default value. We are now having a specific parameter now, and we run that. You can see sgb.classifier, and we have the parameters that we just set up to explore their combination and how it could help us achieve the best parameter combination. So we have this n estimator, max depth, learning rate, subsample, column sample by 3. And for the random search, it's just going to randomly sample the combination, then search through it to get the best. Now we have our parameters defined, and now we need to instantiate the random search CV. It will receive different parameters like the model we want to use, the parameter distribution of the model, the number of iteration. Here we are saying it should go 30 times. Then for the cross-validation, we have 5. Then the scoring is accuracy because we are dealing with classification here. And other parameters are just the regular system parameters. Now, I will load that and then fit, which is where the hyperparameter tuning will happen. I'm not going to take your time, so I'll just wait until this is done. Now the process is done, and the random search took about 2 minutes to run, and we can just print the parameters so we can see. So the next phase will be to then check the grid search, which is the next thing. And for the grid search, we have the same process. We define the parameter grid, and then we initialize our grid search CV using the same process, and we run the fit. While this is running, I'm going to pause the video, then continue when it is done. It is done running. We can see it took 25 minutes to do the hyperparameter tuning using grid search as compared to the one for random search, which took just about 2 minutes. So that just comes back to prove what I said the other time on how grid search takes a lot of time. So here we can print the estimator, and here we can see these are the best estimators that we have. Then we can then move ahead to the Bayesian optimization. And the pattern for the Bayesian optimization is different. For the Bayesian optimization, we are using Optuna. And the first thing is we need to have like a function where we are going to be defining our XGB objective and the parameter ranges. So we have the models, and we initialize it as sgb.classifier. Then within the model parameter, we're going to create our trials. So for n estimators, we have the trials, which is, of course, here it is an integer to suggest the best integer for this n estimator. And it's going to go between ranges that is from n estimator 200 to 800. So compared to here, where in the grid search and the random search, you can see we have 200, 400, 600. Then here we have from 200 to 800. So it will explore between this to find what will be the best. Same as for the max depth, it will explore between 3 and 10. We don't have to tell it 3, 4, 5. So it will explore between 3 and 10 to find the best, and to explore it in integers. Then for learning rate, it will do the same. It's a float. That is, you can see it's a decimal. Here it will explore between 0.01 to 0.1. And for others, it will do the same. Then it will check the cross-validation score and return which one is the best in the end with respect to the parameters. So we're going to run this function here. Then we're going to apply it using this study. We say XGB study, optuna.create study. Then we tell it to maximize. We want to get the best accuracy. Then we optimize the XGB objectives. And the number of trials is 50. So I think let me reduce it to 30. So it is the same as the number of iteration for the other ones. So I'm going to run this and just look at that, the way it runs. Now this took about 3 minutes for 30 trials. And one of the things you will see is it's not just exploring just 200, 400, or 600 like the other. It is exploring far more in between the boundaries concerning the n estimators. So you can see it explores it to find the best. And here we can see the best one will be stored into the xgb study.best parameter. And we can run that. And using the best of this, we can fit our XGBoost model in the end. So you can see now we have our XGB model working perfectly. And you will see the parameter used for that. So you can see here the learning rate 0.05 was found as the best. The max depth, we have 8. N estimator is about 397. Then we have our colon sample by tree around 0.70 as the best. So if we look at this for the grid search, you will see also it found around the same parameter. You can see 0.7, learning rate 0.05, max depth 8, and our N estimator, this found it to be about 200 as the optimal parameter combination. Then for the random search, you see also colon sample by tree 0.7 as the optimal. N estimator is about 600. Then max depth is 8 on 8. Then learning rate is 0.01. That is, these are parameters, hyperparameters that could be used to fit the best of our XGBoost model for our crop type recommendation. Another thing that you need to compare here is just to see the difference between the grid search random search and the Bayesian optimization. Here is you see that this was fitting 5-fold for each of the 30 candidates. So you see totally 150 fit. So it only sampled about 30 parameter combination, then fitting them 5 times based on the cross validation to get 150 fit. But when you look at the grid search, you will see that it is a different ball game. You have 324 candidates. That is, it is every of the combination. So it combines 200 with 3, with 0.01, with 0.7, with 0.7. If you do that, then do 200 combined with 5, combined with 0.05, combined with 0.7. So it will do all those combination before it arrives at everything, making it 1,620 feet. So you can see how that is very exhaustive. So that's the difference in how hyperparameter tuning is done. And since you have the best parameters, you can then train your final model using that and get the best results. So that will be it. If you've learned something from this video, feel free to click the like button and also subscribe if you are yet to do so that you can easily get notified when we have a new video uploaded. So thank you.